Are you guys ready for another wonderful physics problem? This time, we are talking about finding the coefficient of static friction. Even more exciting. Just remember, if you feel like you don't get this, or it doesn't make any sense, all you have to do is remember that this problem is fact, not friction. My dad will take it from here. Thank you, thank you.
Thanks, Hannah, again for that strange and wonderful introduction. All right, here's the problem. A horizontal force of 400 newtons is needed to just begin to move a box with a mass of 80 kilograms on a rough surface. Find the coefficient of static friction. And there's something important to remember here about static friction, and that is that when we're just applying enough force to begin to overcome that force of static friction, the maximum static friction force, F sub s max, we'll write it like that, is equal to the coefficient of static friction times the normal force. And so the coefficient of static friction is a measure of how rough these surfaces are as they're sliding, just beginning to slide across one another. As always with Newton's laws, we start off with a free body diagram. And so we draw a little dot. Here we draw in the forces that act on the mass. First, we know that there's a normal force, F sub n. We also know that the downward force of gravity, the earth pulling on the object, that's F sub g. And the other force is the force that's being applied horizontally, which eventually causes the object to move, capital F. And finally, the static friction force, which is opposing that horizontal motion. And we'll call that F sub s. So there are four forces acting. Okay, we need a coordinate system so that we can write down Newton's second law in all the directions that are involved. So we've got a standard horizontal, vertical coordinate system like that. So, what's the plan of attack? We write down the sum of the forces acting in the x direction. The Greek letter sigma means sum, remember. F sub x, we add up all the x components of the forces, and in this case we get capital F minus F sub s, and whenever we add up the sum of the forces along a direction, we get the mass times the acceleration along that direction, a sub x in this case. Can we do anything more with this? Well, if we understand the problem, it says that we push on it with just enough F, just enough force to begin to let it move. And right as it begins to move, that's when the static friction force is its maximum. Okay? But just at that point, the acceleration is just beginning to increase above zero. And so we're going to write down this equation right on the verge of the box beginning to slide. And so if we do that, we get F minus, and here we're going to write down the maximum static friction force, F sub s max, like I wrote down earlier. And that's equal to, we'll get that maximum static friction force just as the acceleration begins to get larger than zero, but right on the verge of it, it's equal to zero. So we can write down that expression for the maximum static friction force, mu sub s times F sub n, the normal force. And that's added together, we get 0 here. All right, and we know capital F, and we want to find mu sub s, but we don't know the normal force yet. So we're stuck. We have to move on and get more information. And that other information comes from Newton's second law applied to the y direction of the forces that are acting on the object, the y components. Here we have a positive force in the y direction, which is the normal force. We've got the downward force of gravity, otherwise known as the weight of the object, and that's going to be m times a sub y. All right, the normal force we don't know. We're trying to solve for that, F sub n, but we do know that the weight, or the gravitational force, is just mg. All right, and on the right-hand side, what's the acceleration in the y direction? It's 0, because the object's going to slide, when it does, horizontally. It's not going to jump up off the surface. So the acceleration in the y direction is 0. The normal force thus gives us Fn equals mg. Okay, and that we can plug into the first equation. So let's take the first equation, the one that we got for the x direction of the motion, and the second equation, and put them together. So I'm going to rewrite the first equation with the second equation plugged in. F minus mu sub s, and times the normal force, we know, but we found the normal force is mg. So mu sub s mg, F minus mu sub s mg is 0. Okay, we know F, we know the mass, we know g, so we can solve for the coefficient of static friction. This is great, we're almost finished. So F equals mu sub s mg, and now divide both sides by mg, turn it around, mu sub s equals F over mg, and as we plug numbers in for this, we should always plug their units in with them, because then we can check our answer and make sure that it has the right units. Alright, so 400 newtons is the force that's applied. M is 80 kilograms. G, we know, is 9.8 meters per second squared. Meters per second squared. And in the denominator, we have kilograms and meters per second squared. That's the same thing as newtons. So we have for our answer newtons over newtons, which cancels out. And that makes sense because if we remember, coefficients of friction are just numbers. They don't have any units associated with them. If you plug these numbers in for the coefficient of static friction, you get 0.51. And that makes sense. Coefficients of friction are usually values that are between 0 and 1. Sometimes they can be a little bit larger, but normally they're less than 1. So this problem helps us to see how writing a free body diagram for an object using Newton's second law for the x and y directions can give us the information needed to solve the problem. So hope that this has been helpful, and it's the same basic method and problem solving steps that you'll use in many problems involving Newton's second law.